So our first session today in the S4 papers here is actually a digital bond paper. It's leveraging vulnerabilities in Ethernet cards and field devices. And Daniel Peck and myself wrote this paper. Daniel did most of the heavy lifting, so he's going to give you most of the presentation. I just have a little part in it. Let me introduce Daniel. Daniel Peck is an offensive security researcher at Digital Bond. He does a lot of our application assessments. Some of you may have read some of the results from the OPC UA security assessment. Daniel did a lot of that. He's also a contributor to our Portal Edge and Quick Draw projects. Before joining Digital Bond, Daniel worked at SecureWorks, which is an MSSP. So when things went wrong in one of their clients and things got hacked, he got to go in and figure out what happened, how to fix it, and how to prevent it from happening again. So he's seen a lot of bad stuff happen. I want to just get us all on the same page at the start here on terms. In this presentation, we're going to use the generic term field device. We're talking about anything that's a PLC, RTU, PAC, IED. We're just going to call that a field device. Some people will call it a controller. Everyone seems to have their own name for it, but just so we're all on the same page, that's what we're calling a field device. And I'm sure most of this audience knows, but today if you buy a field device, there's a good chance that it has an Ethernet card option in it. Very few successful field devices don't offer that option. That doesn't mean all field devices are connected via Ethernet. Still, the majority of them are connected via serial, but the trend is pretty clear that more and more connectivity via this Ethernet card is going to happen. Originally, it'll be for HMI and control servers talking to field devices. In the future, field device to field device communication, field device to instrument or sensor. It's a growing trend. And I think most of you know today there's minimal, if any, security in these field devices. To date, the work done on attacking field devices has really fallen in two different areas. One is there's a camp that has been fuzzing field devices, sending malformed data, either intelligently or just random data at a field device and seeing if the network protocol stack crashes. There's a couple companies, Mu Dynamics, WorldTech, that offer products that do that. A lot of people that do assessments will fuzz the control system specific ports and see what happens. The bad news is, if you follow this, a lot of field device protocol stacks will crash. They're getting better, but it is an ongoing problem, and you've seen some research in that area. The other research, and this is not new, has really been more just a demonstration that field device protocols don't have security. I saw this first in about 2002 with Eric Byers at an ISA Expo where he had his attacker Modbus TCP client talking to some field device that made lights go on and off, and he showed how an attacker could make those lights go on and off just because the protocol had no security. And we still see that presentation being made quite a bit. It's now migrated from the control system world to various black and gray hat conferences. And that's what's called attacking SCADA field devices. So one of the things you look at is, if I'm able as an attacker with logical access to a field device, if I can ping that field device, if I have the capability of reading all the values in that field device, doing the diagnostics, and even writing changes to that field device to change a process, if I can do that, all that as an attacker, why do I care about anything else? I think someone yesterday said it's game over. If you can get to the box, it's game over. Well, we thought about that a little bit, and we said, well, maybe there are some reasons why you'd want to do more than that. One is you may want to stage an attack. So maybe you want to compromise a system and have an attack happen en masse at the time of your choosing, such as 11:58 on New Year's Eve, or right before the inauguration in Washington, D.C. So maybe you want to pre-stage something. That was one reason we had. Another reason is, what if these field devices could be used as attack platforms? So maybe our target isn't the field device, but maybe since these field devices are throughout the control system, maybe we can use those as attack platforms to go after other field devices, servers, HMIs, and a variety of things on the control system network. So that's what led us to pursue this line of thinking. And in this talk, we're going to talk about two different attack vectors. The first is a rogue firmware load. If you have the ability to load your own firmware onto an Ethernet card in a field device. First of all, how do you do it? Can you do it? What can you do with that? And secondly, we looked at the management applications, the web servers, FTP servers, SNMP servers. We said, okay, can those be compromised? If they are compromised, what can you do with it? And that what can you do with it we'll talk about a little bit later. But to start up, we wanted to actually talk about some of these attacks and how they're accomplished. And we had two field devices in our lab that we actually ran these attacks against. And I'm going to let Daniel go into that detail.
Right. What you got there? Let me clicker. All right, everybody. First up, we're going to, mic's working ever? Good. All right, first up, we're going to talk about our first device here. It was Rockwell Automation. I'll move a little bit to get out of that spotlight and block the screen. Rockwell Automation ENBT 1756. Pretty standard Ethernet module, not a lot to it. We approached this in a very black box fashion. We bought the devices, that's all we had. Didn't have any particular insight or any particular experience with these or any other Ethernet modules in particular. We just sort of went to town on it with what we had. So first up in our analysis, I want to talk a little bit about the tools of the trade, what was used to do it, and then we'll get into sort of how we do it. The most basic tool is a hex editor. This allows us to just look at a binary, see all the hex codes, find the strings in it, find some offsets later on, to figure out what's at each particular location and really start to do some analysis of the binary and find out exactly what's in it. There's dozens of different hex editors. Hex Workshop happens to be mine of choice, but it's pretty much anything that displays the binary for you, nothing special. As we got a little bit more advanced, we moved into using a disassembler. IDA Pro is pretty much the industry standard, and for anyone doing disassembly, that was our tool of choice there. The flashing software we used, while we could have written our own stacks, we decided to save some time and use the vendor-supplied ones. Since they're just using standard TCP connections and virtually nothing more than a little obfuscation, it would be very easy to duplicate this. But to save ourselves a little time, we used the control flash provided by Rockwell and the net edit provided by Automation Direct/Koya that we'll talk about soon. We also started off with several copies of the firmware. These are easy to download from the websites of the vendors in question, and that allowed us to do some comparison and see some static fields and things of that nature as we went through the analysis phase. So first steps, dropping into a hex editor. What do you see? Well, not a lot. You see a lot of garbage here. This is the hex. But over here you start to see ASCII. If it's printable characters, it'll display that for you. Looking through, you see a lot of garbage, a lot of junk, stuff that doesn't mean anything. But we get a little bit lucky towards the end. See some HTML in plain text. That means at least part of the binary is not compressed, not encrypted in any way either. So that was good. But not all the pages were there. Due to playing with the device some before, seeing all the capabilities, I could tell that not all the pages, not all the abilities of the device were displayed here. So there must be something more. So we started looking at that a little bit more. First step is to really see if we can change it. So that's really what we were after with this. So keep it simple. We found the HTML in there. It's very easy to change HTML. Nothing too fancy to it. There's no dependencies. You just change the text. So we do that and try to upload it. No luck. Control Flash won't allow it, complains about it. Doesn't really give you a very good error. So we have to do some more analysis. There must be some sort of checksum, some sort of encryption routine, something blocking it. But we'll find it. So we started to analyze the binary a little bit more. And there's some common compression techniques that are used in pretty much the embedded world all around. In control systems and wireless routers, you're going to find a lot of this. And that's zlib, compressed blocks of binary data. Zlib is a compression technique that's been around for quite a while, several decades. It's very fast, very efficient. Doesn't do anything too special, but it's just a very good, very common encryption routine. Using a tool DZ, which is really just a couple of, maybe a 100, 150 line C program written by Montesano. It searches through the binary file you give it, looks for the headers of these zlib compressed blocks, decompresses it, puts it in another file for you to analyze. Nothing too special to it, just looked for compressed data and hands it to you. So we got lucky, we found one. So now we have another meg and a half of binary data that we're looking at. And we start to look through there, and we get lucky. Because when you start doing when you find all the strings in a binary, they start to look a little interesting. Here we see things AB underscore exit, AB init, close and free all connections, copy element responses. These things look a lot like function names. It's a symbol table. So we have a good idea of what the functionality of the device is just by the names of the functions. Have a good idea of how it works. And there were quite a few of those functions. Not an insignificant amount, several thousand. It's a fully fledged operating system running on that. There's a lot of things that it does. We also, but to really use that, we need to find the offset table. We need to figure out where those symbols live, where they're pointing to. And this was pretty difficult to find. Had to look through the binary quite a while. But after you look at it for a while, and between the time that your eyes cross and you start getting a headache, you start to see patterns. So here, if you'll look, I've highlighted the 0, 0, 05, 0 in hex. Start to see a pretty regular pattern of that at certain stages in the file. And the addresses, or the bytes before it, look an awful lot like addresses. Turns out they were. I can't remember if it was the first one or the second one, but one points to the symbol table entry we found before, and one points to that where that exists, that code exists. So we've got our offsets. There was also a flag structure in here somewhere. Oh, the 0500 was a flag structure. Never ended up really needing to know what that was. There were a few that had different than the 500, hex 500, but that didn't really affect us much. They were all still functions. So it was almost time to load into IDLE. But we still didn't know what kind of processor it was. Originally, I had assumed ARM, because there's a lot of ARM chipsets out there. But we really didn't know. And IDA didn't really like it when I told it ARM, so it was time to go back to the drawing board and figure out exactly what it was. Google didn't provide much assistance either. There was no real documentation with any of the Rockwell documents or anything available online about what kind of processor would be in this. So without just random guessing, I had to look a little bit more. Once again, thanks to the symbol tables, looking here, we see R0, SP, R2, R3, R4, some FRs up there. These are registers in PowerPC. Any of you that have done assembly work before, be very, very recognizable. So, instantly we knew PowerPC. Go time. After investigating this some more, we found PowerPC is actually really popular in embedded systems. Honestly, I had no idea before doing this sort of analysis. But they do quite a bit of work there. There's a lot of these smaller embedded chips that are just mass-produced, small PowerPC, low megahertz, but get the job done. PowerPC is RISC-based, very simple instructions, not many of them. They only do one thing, all fixed number of bytes, things of that nature. Turns out the exact chip, after I bricked one of the devices and decided to take it apart to see what was in it, It was power quick. Like I said, low megahertz, 50 megahertz chip. Nothing too fast, but you can get the job done. We also found through a little bit more of the binary analysis that I won't get into, but VxWorks 5.5, that string appeared pretty regularly and told us exactly what we were looking at and gave some help later on in the disassembly. So loading it into IDA, we write a quick script. IDA has a scripting language included with it that allowed us to associate the symbol table with the memory addresses we already found, and boom, we're looking at a full disassembly pretty quick. We're really getting somewhere now, and for those of you who are familiar with disassembly, you know that's as good as source code. It takes longer to read, but it's every bit as good. So here's the look at what we had in IDA. And remember, at this point, we're still trying to find our checksum or something of that nature so that we can load our firmware. So after looking through our function names that we found, we find some that are kind of interesting here. There's one NV underscore RAM validate checksums write flash. Looks good. And here in this screen we have our disassembly. You can see the PowerPC commands. Nothing too fancy. It's moving memory addresses, it's adding stuff, it's calling other functions like memcopy here. And FFS calc checksum, another interesting function. We found that the RAM validate checksum write flash actually called the calc checksum twice. Something we probably wouldn't have been able to find with just straight looking at the binary if we hadn't have done this disassembly. Here's a little bit closer look at the disassembly if you couldn't see it very well. Show the 2 times calling the checksum. And here's a list of just a few of the functions that we've got now. There's some interesting stuff here. Like we said, the most interesting already is the validate checksum. So after a little bit of reverse engineering that I'll spare you the details on because it's honestly not a very good spectator sport and it's pretty tedious to do even yourself. But we found that there were two 2-byte checksums. One for the whole file and one for just the header. Here we see the header structure, our offsets. The very first, you have the header checksum, that 9595. The size of the header is there at hex C. The file size we found because it was constant across all the different versions of the firmware we had. So that was pretty easy to tell when you do a little looking up of what those numbers equal. That was the file size there in the header. And then the file checksum, right there, 14. So where are we? Well, we got our checksums. We can now upload arbitrary firmware. We were able to embed malicious scripting, code, things of that nature, into the web management console of it. Have it deliver arbitrary JavaScript, Internet Explorer exploits, things of that nature. We also have produced a proof of concept ping shellcode for the device. Next up, Koyo H4 Ecom 100. Very similar device in the fundamentals of it. A little bit different in how it does things. It's used a lot more for management than it is for just getting information like the Rockwell device was. So we're going to look at that a little bit differently, just to give it a different flavor of how to do things. This one we did totally black box. It was all about sniffing the firmware to start off with. Just had the net edit tool, uploaded to the latest firmware, or updated to the latest firmware from what we had shipped to us. Wireshark didn't really know what it was. It's just a binary protocol to it. Couldn't decipher it at all. Here we see what we saw in Wireshark. It's just UDP. Can't do any real analysis for us. So we were on our own. So we start looking at the protocol, and we see a few things that are pretty common. There were some timer values, nothing too big, but this HAP string appears at the start of every one of these packets. And that gave us somewhere to start looking for stuff. Like I said, not a common protocol. but it's pretty hard for stuff to disappear on the internet. And if it's a protocol, somebody's written a spec at some time about it. If you know the right things to look for, Ecom Ethernet interface specification. This was found on a small consulting site, library of PDFs. I believe the company itself has been out of business for some years. Looking through this PDF, 11 pages, very simple protocol, very common functionality as far as control system protocols go. Read points, write points, time sync, nothing too special. But we're able to very clearly understand it all. It was interesting that it also worked with multicast. There were some fundamental differences with the protocol in that it sent everything multicast and responded back. But it also worked direct. So it was able to work not only on local networks, but anywhere routable. Had similar results with this device after that. Able to upload modified firmware at will, embed malicious HTML, JavaScript, things of that nature. Fully modified code is possible. This device was running on an FPGA chipset, NIOS, distributed by Altera. It would take some pretty significant work to completely analyze that binary, something that was out of the scope of the time we had, but with the ability to upload arbitrary firmware pretty much already there. Custom processor module would have to be developed for IDA Pro, as none existed to disassemble the NIOS chipset specifically, but it was there. And since we were already able to modify the code, pretty much points have been proven. Hand it back over to Dale here.
Thanks. So this is just two of many examples of field devices that allow unauthenticated firmware upload, and going through the details to show exactly how, what Daniel did, how an attacker would learn the load and be able to load their own software on it. We then looked at, well, what would someone do with this capability? Always with the lower bar saying, well, if it's no worse than just being able to read or write to the field device, then it's really of no value going through the trouble. So in this case, you're really just limited by your imagination as a potential attacker. And I'm sure some of you in the audience probably will have ideas well beyond and maybe even nastier than the ones we came up with. But we sat down and talked about it a little bit and came up with some ideas. I mentioned this one earlier, the concept of a delayed attack. So we get into the network, we're able to load our own rogue firmware. We may decide we're going to brick the box or send the process to a bad state, cause constant reboots. We could do a variety of things, and we could just set up a job to run that at the time of our choosing. We also looked at this as a case of if someone compromised these field devices on your network and wasn't ready to do anything now but didn't want to lose the capability, they could have in the firmware something that says, if you don't hear from me every week, launch this attack. So they might want to hold their fire until a time of their choosing or until a time when they no longer had access to the device because maybe a firewall got fixed or put in place. So the delayed attack was one scenario what we thought of. Certainly we did this by accident, but it's not hard to brick the Ethernet card. So if you had control of a variety, some or all or most of the field devices, loaded your own firmware on those field devices, you can just load firmware that stops working correctly and no longer allows other firmware to be uploaded. Essentially a return to factory condition and replace the Ethernet card. Now in a control system, if you do that to just one field device, inconvenient, but there's spares and redundancy. But if you do that to all of the field devices or a large portion of them, you may not have enough spares. It's going to take you a while to replace those things. In a SCADA network, you got to go through all that travel to get out there. It could have a nasty little impact. We also looked a little bit at the insider attack. And one of the things we thought about here was there was a paper last year at S4 by Ralph Langner and Brian Singer talking about why we don't see catastrophic attacks on control systems. And one of the reasons they said was a lot of people that could do those don't want to cause a blackout for a region or, you know, no drinkable water for a city. They don't want to do that type of damage. They're not that nasty, and or they're afraid of getting caught. You know, it's one thing to cause a little problem. You cause a region-wide outage, they're going to look pretty hard for you. There could be some serious consequences. But what about the disgruntled insider who just is really ticked off at a boss or a new guy that came in and just wants to cause problems? One of the things we thought of is you could have a list of things you could do on the device. So you could brick the device. You could cause the device to continually reboot. You could cause it to be unavailable, random process changes. You could have all these different things in the firmware that you could do, and then just have a random number generator, pick one of them, pick a delay on when it's going to be run and a duration for the attack. And if you did that on a number of devices, you'd have all these little intermittent, non-correlated things going on in your network, and you'd really cause the operations and engineering staff to go a little crazy. That would be really hard to track down. So maybe a really clever disgruntled insider could have some fun. We looked at a field device worm. And in fact, we're developing a proof of concept field device worm. The idea is if you're able to upload firmware, let's use the control logics just as an example. If you're able to upload firmware to one of these devices, right now we're pinging other devices, but we can do a port scan looking for other devices that have the Ethernet IP port open. Good chance that's a control logics device. Our compromised field device then uploads the firmware to that other one that it found and all the other field devices it finds, and then does whatever the attacker chooses. So in this case, if you were able to get logical access to one field device, you'd be able to compromise all the field devices. And you could set up something like a field device botnet if you wanted, just sitting there ready for your use. As I said, this is the proof of concept worm we're doing is just pings, just port scans a device, finds it, uploads its firmware, reports back that it's ready to go. The other thing that we looked at is, could this, and I mentioned this earlier, could this field device that we've compromised, this Ethernet card on the field device that we now have control of, could that be used to attack other things? And I think there's a really good analog to this in the corporate security world with printers. You've got these devices that nobody really pays attention to. You're patching your OSs every month. When they come out, you're worried about that. Your printers, they just sit. No one really bothers them. Field devices are more critical than printers, but they sort of have that same approach. They get out there and nothing really changes for a long period of time. So if you could use those as attack platforms, there's a good chance once you're on there, you would not be noticed because that firmware is not being repeated over and over again. So you could use it to attack other field devices, or you could use it to attack your real-time servers, your OPC servers, your HMIs, your engineering workstations. You could use it to look for unpatched Windows systems and run exploits from your field devices. So it's, like I said, it's very similar to a printer methodology. Now, I want to be clear on one thing here. We talked about two field devices today, but this is a problem across most of the field devices that have Ethernet cards. They have this feature that allows unauthenticated firmware upload. So if you have a field device that allows unauthenticated firmware upload, there's a good chance that someone like Daniel or probably half the people in this room could learn to load and load their own rogue firmware on there. So it's really an industry-wide problem. The solution is pretty obvious. We need to authenticate the source and the content of this firmware before we load it onto that Ethernet card. And one obvious way of doing this is with a digital signature. That would cover both those areas. It's probably going to be a little while before that capability is out there. So you really have to ask yourself, if you've got these systems out there, is there a way to disable the capability of doing this firmware upload? And talk to your vendors and ask them how you're going to secure it or how you're going to stop that. there is a reason why this remote firmware upload is in there, because it makes a lot of sense in a SCADA network. It can save you a lot of time and money in traveling. So you can understand why it was put there in the feature. It just wasn't secured. Now, we did want to talk about one other area in a little less detail about another set of vulnerabilities, and that's in the management applications.
So the question we asked ourselves here was, what if all that didn't work? What if these devices, the firmware upload was completely secure? What if all that worked? So we started looking at the management service interfaces to the device. And this varies by device. Today we're going to be talking about HTTP, a little FTP, even into SNMP and things of that nature as well. But they're pretty standard stuff on control system network. So looking at the web servers to begin with, it's cross-site scripting, first of all. I assume everyone's at least vaguely familiar with cross-site scripting, being able to run arbitrary scripts from the web server to whatever client's connecting it. This is used in a lot of attacks that deliver malware. It's all over the web. It's the most common vulnerability that exists these days. Cross-site scripting is just everywhere. It's ubiquitous. And it's a very easy way to attack desktops and anything else that would connect to these ports. By doing that, we could attack HMIs that would connect to it, or anything else. We also, through cross-site scripting and a little bit of URL fudging, were able to access config files on the device that we shouldn't have been able to read. This is very similar to the directory traversal attacks that used to exist quite a bit on the older web servers in the traditional IT security world. These config files told us quite a bit, things like usernames and passwords, even though these devices didn't have anywhere to log in. Something to think about. We'll get back to that in a second. It also told us some of the other services that we're running, and you configure some of those services because we can already upload firmware now, so we could use this ability too to change these services around. Here's some examples of the cross-site scripting. This device particularly didn't sanitize the input at all, and anyone who connected to it could change the module names, module IDs, things of that nature. This is just a simple proof of concept. Pops up a little window that says cross-site scripting. Nothing fancy, but was very easy to do, very trivial to do. And you could do that with pretty much any input place on the web interface. Orphan code is also an issue on some of these devices, and it's an issue on a lot of embedded devices, because a lot of times the vendor is provided by their upstream vendor with, here's a binary, here's an API, bolt whatever you want onto it and go. Well, some of the times the initial package delivery might have some stuff that the developer is not aware of, might not know what to do. The 1756 module contained full FTP server that was undocumented and apparently not known to be in the code. But by changing a simple config file in the firmware, we're able to activate it. We were then able to use the username and password we found to log in. We were able to cause quite a few crashes with that, and didn't really get into that much further, but there were both pre-auth and post-auth problems in that arena. Doing this sort of thing opens up the devices for a wide range of attacks. The FTP server specifically could be used as a kind of a staging point. You could hold any kind of data there. You could bounce data off. You could hold potentially malicious or illegal information there. It's used quite a bit in traditional IT security. People who have, well, let's say, not very clean information or pornography, things of that nature, can hold it on the device. Not exactly the kind of issues we're generally concerned about, but if your devices are able to be used to store arbitrary data and you don't even know that they can, that might pose some problems. So in conclusion, talked about a few things here. Asset owners, the important thing is to determine if your field devices can have this arbitrary firmware upload, what can happen to it, how to disable it, how to monitor it if nothing else. Vendors, source and content need to be validated before this is uploaded to the device. You need to make sure that it knows what it's taking in, and to everybody. The important thing to think about is these devices, as they get smarter and smarter and running more and more services, be it web servers, FTP servers, SSH, Telnet, etc., bigger and bigger attack space. And it has to be more and more attention paid to it as these devices get smarter and smarter and the possible consequences increase.
So we'll open it up for any questions, comments.
Ralph Langner from Langner Communications. So first of all, great presentation, excellent work. Thank you very much for that. I have one question in respect to strategy. The first part of your presentation where you explain how you were able to load rogue firmware onto the device. Well, that makes sense in respect to the attacker target of just bricking the Ethernet card. But when it comes down to process manipulation, I asked myself, why didn't you choose the direct way of manipulating the ladder logic? Why not just go at the ladder logic? For example, you could do code injection there as well.
Right, you could. This was just focusing more on the firmware. It wasn't, we just didn't take that route. This was just looking at other mechanisms. But yes, the control logic, the ladder logic be uploaded in a very similar way and attack the back-end control of it that way as well. Looking at the firmware was more to add more attack capabilities later on and run those processes, or run our own processes on it outside the scope of what was already there.
More as using it as an attack platform for other things rather than for the PLC. Yeah. Well, and what you bring up is a good point, is once you realize you can do this sort of thing, it really is just restricted to your imagination.
See, what we've shown here is I had no knowledge that you could do that with ladder logic, but I was still able to do this as someone with no experience in the control logic's RS-Link specific world of doing things.
Jason, is there a virtual question?
Yeah, we have a question from Donovan Tyndall from MajorCon, who's up in Edmonton. It's about how the environment was set up. He said, Daniel stated that he fired up Hex Workshop, but what exactly did you open? And was this a TCP/IP stream or looking at the firmware? Just wanting to get a bit more information about what you were looking at with Hex Workshop and how you did that.
Hex Workshop was looking at the firmware itself. These were the firmware files that were downloaded from the vendors, and used Hex Workshop to analyze those. The packet streams that were analyzed later on in the presentation were done with Wireshark, which is essentially a specialized Hex Editor for network traffic.
Julian Rushi, Ornell, Oak National Laboratory. I need to share some experiences with you. All right, so we're talking about loading firmware. So I'm assuming that the shellcode is loaded in the program segment of the random access memory. My question to you is, do these field devices have an executable stack?
Well, that's going to depend on the different field devices and what kind of chipsets they're running. It really didn't matter in this case because you're able to upload your own firmware. So it's before it's even loaded into memory. So that really didn't matter in this case. But some devices would have an executable stack. We're seeing a lot of PLCs. There's a lot going around about changing to x86 as kind of the base chipset, the base processor in use because it's such a commodity processor. You don't have to worry about it being obsolete. You don't have to worry about costs going up or your vendor saying, I'm not selling enough, I need to discontinue this.
I noticed that you were able to map symbols from the symbol table to memory addresses, and you were doing static analysis.
Right.
So that tells me that there are no dynamic libraries there. Is that true?
As far as I know, and I'm not a VxWorks expert by any means, though I learned an awful lot going through this. The libraries are loaded up as part of the packaging and they're not dynamic, so to speak, because they're already in memory, but they have to be called from each individual thread or process. VxWorks doesn't work in the traditional threads model exactly, but it's kind of similar. Everything is one process for the most part, but it has to have access to those that are included with VxWorks. There's like a socket lib and things of that nature. So they're already there. They just have to call specifically to them. And something to point out with the symbol table also is that you can't remove this. I won't say that's a complete fact, but I talked to a lot of people who have done VxWorks before and tried to sanitize their binaries for various embedded systems. And too much of it depends on connecting those strings to the functions when you're making certain calls. And they're just not able to take that part out.
Jason, is there another virtual?
Yeah, we actually have a couple of people are asking about how we can detect when this rogue firmware upload or happens or when something changes on the device.
Well, that is a problem that needs to be addressed by the vendors, actually. As it currently stands, at least with a lot of the devices we looked at, or all the devices we looked at, there's no way to say, give me the firmware that you're currently running so that I can see what it is. This is something that they've also dealt with kind of in the router and switch world, and Cisco IOS now allows you to at least get some information about what's running there. That has to be available, especially if you're not validating what's being uploaded beforehand. At least allow whoever's requesting information about what's running to know what's running.
But yeah, my name is Evan Han with I do believe there are ways to do validation.
I think one comment on that, because we looked at a scenario where you could load rogue firmware, and then that firmware could report back that it was still running the version you thought it was. And then even if you went to make a change, it could send back a message saying the change was made and report back the number you expected, while in fact you're still running whatever you think. I mean, again, it really, once you have that level of control over the system, it's hard to stop someone.
Jake Brodsky, Washington Suburban Sanitary Commission. Just a quick question. How long did the firmware update take? How frequently should we be polling these cards, and could we possibly detect the fact that somebody's doing something by a card that goes away and then comes back?
That could be one way of detecting it. It depends on how often these cards are coming up and down in your environment. Some things we saw are that you can, one particular device, if you sneeze too hard next to it, it's going to fall over. So it was rebooting at a fairly constant rate just with standard network traffic. But the firmware upload took about 30 seconds, in which the device was still accurately acting like that, and took anywhere from 30 seconds to 60 seconds to reboot and come up after that.
So you're looking at a period of time of, what, 120 seconds or so?
Maybe. Something in that range.
We'd notice an outage like that. We wouldn't do anything with it yet because obviously we weren't aware of the problem until now.
That could be normal network traffic and failure on most of these devices. It doesn't have to be, not necessarily indicative of a firmware update or down the.
Well, just let's try to use the mic so that the virtual people can hear us. Did you want to?
Sure, I'll repeat the question. Yeah, I guess you see failures like that on industrial networks all the time, and nobody thinks anything of it because usually it could be just even a layer 2 network could be dying for just a few seconds. It's not indicative of firmware flash in any stretch. The only way I could think to possibly do that would be to have some type of intrusion detection signature that's looking for very specifically that on an individual node. So I mean I actually look at like the firmware update on a control device. I don't understand why somebody would do that when the most likely scenario, if from an insider perspective even, would be to download the available programs out there and just monkey with the settings. I guess where I would see a lot more risk in this, though, is you look at like remote field devices, for example, like automated meter readers, for example, and the idea that I might be able to brick an entire section of the grid by being able to go in and download a bad program to a bunch of meters, and there's no way at the processing power on those devices you'd be able to have a signature to even check for that. So, I look at something like this, while very interesting and obviously proving a point, At this class of device, I don't think I'd even look at this too heavily. I'd be looking at it further down the stack where we know it's a lot more realistic that you could never stop it. So anyway.
And something to address what we talked about with the rebooting and detecting it, what do you do after that fact? Because you can also embed it in the Ethernet industrial protocol, and SIP is reset messages. You know, you could have somebody just completely mess with your engineering team for any amount of time because you have to allow that command through.
Howdy, I'm Travis Goodspeed, private citizen. So a couple of technical comments on VxWorks. With version 5.5, it can be configured by the vendor to have separate updates for the application and the operating system. So I worked with a particular device where the application was loaded. And while it had symbols intact, that's not a requirement. You can strip it and it runs fine. Using open source GNU tools, you don't need to purchase the development tools from Wind River. Also, with that application image, IDA Pro will automatically identify function symbols and all that stuff. So you can strip it out. You can validate this application then, because if you add a signature to it, that can be checked before the application is loaded and after the rest of the firmware has been loaded.
Great. Thank you. Did I miss anyone? Anyone else before we give Julian a second try? Oh, you've had your first try too.
All right, so we were talking about cross-site scripting. So the attacker has to be able to store malicious script code in a server that is then viewed by others.
Right.
Did you see any module that logs who modifies what?
I saw no evidence of that in
Right.
the devices we analyzed.
So any user could attack any other user without leaving any traces behind, right?
Yes, and of course you could have network logs if you have your router or switch or some sort of IDS, IPS system monitoring connections. You could have some information there about what IP it came from, but that would also just an IP in no way associates to a user because there was no authentication needed to log into the device before inserting these cross-site scripting requests.
Did you have? Yeah, okay, we have time for one more. Give Evan another shot here.
I guess I see the research being done in individual devices. I guess the question is anyone looking at total systems that do have at least the controls equivalent of IDS on them already? I mean, an entire system to see if they are caught or not.
It's a good question. The only thing in the shameless plug category is that one of our research projects, QuickDraw, this is how we kind of got more interested in this, is we are enhancing an IDS to detect messages and create security events, and there are some of those around firmware uploads. So that's the only thing I'm aware of, but there's probably more. So I think with that we'll end the first session. Thank you very much, Daniel.